So we're going to solve some more linear homogeneous constant coefficient recurrence relations of order 2. Remember, they all look like this. And our algorithm tells us to first solve this quadratic equation where the d's come from up here. And there are two cases. One is the quadratic equation has distinct roots. And we looked at that last time. Case 2 is where the quadratic equation has repeated roots, R1 and R1. And that's what I'm going to concentrate on this time. So we're going to go down to our second example. First one of this video. We're going to solve a sub n is 4 times a sub n minus 1 minus 4 times a sub n minus 2. And of course that recurrence relation is good for n element of the set 2, 3, 4, etc. The initial conditions we're going to use now are a0 is 4 and a1 is 14. All right, what did the algorithm say? First, I solve a quadratic equation. Since this coefficient here is 4, the coefficient down here is minus 4. And since that coefficient is minus 4, this coefficient is 4. So I solve the equation r squared minus 4r plus 4 equals 0. Well, it's pretty easy to see that that's a perfect square. R minus 2 squared is equal to 0. By the way, if you cannot factor it, you could use a quadratic formula. You need to recall what that is. The point is that I have a repeated root 2 and 2. And if I have a repeated root, then I'm actually in case 2 from our algorithm. And case 2 tells me that I expect a solution of the form c1 to the n plus c2 and n times 2 to the n. And all I have to do is solve for the c's. Well, I do that by using the initial conditions. And my initial conditions were a0 is 4. So I take this equation, I plug in n equals 0 to get a sub 0. I know that's 4. Plugging it in, it becomes c1 2 to the 0 plus c2 times 0 times 2 to the 0. This term, of course, is 0. So the thing cleans up to be what? C1 is equal to 4. Well, that's great. So now I already know what C1 is. Now I need to solve for C2. I plug in my second initial condition, which says A1 is 14. I plug n equals 1 into this equation to get this. After I clean things up, I get 14 is 2c1 plus 2c2. But of course I know c1 is 4. Plugging that in, I get 14 is equal to 2 times 4 plus 2c2. Hence, c2 has to be 3. So now I know what C1 is, I know what C2 is, I know my solution looks like that. So I plug it in and I get my final answer. It's equal to 4 times 2 to the n plus 3n times 2 to the n. Now again, this final answer, which is the thing solved, should be good for all n element of the whole numbers starting at 0. So again, just to be sure I did my arithmetic right, I can check to make sure it works for at least the initial conditions. The initial conditions, you recall, was A0 is 4 and A1 is 14. Well, when I plug in n equals 0 here, I get this. And that cleans up, since this is 0 and 2 to the 0 is 1. I get, sure enough, A0 is 4. I plug in n equals 1 into this equation, and I get A1 is 4 times 2 to the 1 plus 3 times 2 to the 1, which cleans up to be 8 plus 6. Lo and behold, is 14. So at least my answer given here works for my initial conditions, and again, I claim it works for every term in the sequence. So finally, that is an example where I have repeated roots. That's all I have to say for now. Have a good day.